In this video, we're going to go through 10 examples where we verify trigonometric identities. So see if you can pause the video and try some of these problems on your own. We'll go through all of them together. And at the end of the video, I'll show you a little bit more about where some of these trig identities come from so you can understand it at a little bit deeper level if you're interested in that. So let's dive into the first example. 1 over secant x plus 1 minus 1 over secant x minus 1 is equal to negative 2 cotangent squared of x. So how can we basically prove that this is an identity, meaning that the left side and the right side are identical to one another? Well, the first thing you want to do is you want to pick the side that's more expanded. It's a little bit bigger, and it's a little bit easier to work with that more expanded side and then condense it down to the side that's more condensed. So in this case, it looks like the left side is a little bit more expanded. So what we're going to do is we're going to try to combine these together into one fraction. Notice there's like two groups here. We only have one group here. So to do that, we're going to get a common denominator. So over here, I'm going to multiply this fraction by secant x minus 1. And I'm going to do that to the numerator and the denominator to keep the fraction the same. And the same thing over here, I'm going to multiply this fraction by secant x plus 1 to the numerator and denominator. And so now if we do that, you can see we're going to end up with secant x minus 1 over, now when I multiply this together, I'm going to get secant squared x minus 1, because notice this is a sum and difference pattern. When you FOIL this out, the inside secant x and negative secant x are going to cancel. You're just going to end up with secant squared minus 1. And then same thing over here with this fraction, we're going to end up with secant x plus 1 all over the common denominator of secant squared x minus 1. And again, we're trying to prove that it's equal to this negative 2 cotangent squared of x. So we're just going to work with this one side and show that it equals that right side. So now that we have a common denominator, we can go ahead and subtract these numerators. So secant minus secant, that's 0. Negative 1 minus 1, that's going to give us negative 2 over secant squared x minus 1. Now when I see these trig functions to the second power, like squared, I like to think of these Pythagorean trig identities as possibly being able to help me. And I notice here that 1 plus tangent squared equals secant squared, but if I subtract 1 from both sides of this equation, secant squared minus 1 is going to equal tangent squared. So this is going to really be negative 2 divided by tangent squared of x. And then you want to use your reciprocal identities. These ones you already know, like 1 over tangent is cotangent. 1 over tangent squared would be equal to cotangent squared. So this comes out to negative 2 cotangent squared x. And you can see they match. We proved it. See if you can pause the video and do example number 2 here. We have sine to the 4th x times sine x cosine x minus sine squared x times sine x cosine x equals negative sine cubed x cosine cubed x. How would you do that one? Well, one thing to notice is that the left side is much more expanded than the right side. So let's go ahead and work with this left side, see if we can condense it down. And what I would do in this one is I'd recognize that I have like two groups, this group and this group, separated by this minus sign. And when we're doing these trig identities, oftentimes you'll find that it's just like doing algebra, but with trig functions. And so what we can do is we can actually do some factoring. So I notice that I've got a sine x, cosine x in both groups. I also have a sine squared x that I can factor out. So what I'm going to do is I'm going to do like the distributive property backwards. I'm going to factor out a sine squared x, sine x, cosine x. And I'm going to factor that out of this group right here and this group right here. So if I factor it out, what will I be left with? Well, I'll be left with sine squared. And over here, I'm factoring that whole quantity out, so I'm just left with minus 1. Okay, so now what can we do? Well, when I see these ones to the second power like this, squared, I think of the Pythagorean trig identities. Sine squared minus 1. Okay, let's see. So sine squared, if I subtract 1 to the left side of the equation, subtract the cosine squared x to the right side, sine squared minus 1 is going to equal the negative cosine squared of x. So we can replace this quantity here with negative cosine squared x. So now let's see what we have. We have sine squared times sine to the first. That's going to give us sine cubed x. Cosine times cosine squared, when you multiply, you add the exponents. 2 plus 1 gives us cosine cubed x, times a negative 1 gives us a negative sine cubed x cosine cubed x. And that's what we were trying to prove. So in this example, it was more of like a factoring example in addition to using the Pythagorean trig identity. Okay, see if you can try number 3. Go ahead and pause the video. We've got 1 plus sine x over cosine x plus cosine x over 1 plus sine x. We're trying to prove that equals 2 secant x. So you're probably noticing a pattern here. Most of the time we're condensing the left side of the equation to equal the right side, but it can be the reverse. But in this case, it looks like the left side's more expanded. You notice we have two groups, just one group over here. So let's see if we can combine these into one fraction by getting a common denominator. So here it looks like the common denominator is going to be the two of these denominators multiplied together. So what I mean by that is this one has a cosine x, but it's missing a 1 plus sine x. So let's go ahead and multiply the numerator and the denominator by what it's missing, which is that 1 plus sine x. Okay, now over here, it's missing a cosine x. So let's multiply the numerator and denominator by cosine x. And let's see what we get. So here, I'm going to leave the denominator in factored form. So this is just going to end up being cosine x times 1 plus sine x. In the numerator, we're going to have to distribute. So we've got 1 times 1 is 1, plus 1 times sine is sine x. Sine x times 1 is another sine x. And sine x times sine x is sine squared x. Okay, plus we have the same denominator here, 1 plus sine x times cosine x. And then we multiply the numerators together, we get cosine squared x. Now, because we have the same denominator, we can combine these into one fraction with a common denominator. So what I'm going to do here is I'm just going to make this into one fraction with this common denominator. Okay, so now let's look at what we have here. We have sine squared plus cosine squared, which is equal to 1. So what I can do is I can combine this sine squared plus cosine squared equal to 1. We've got 1 plus 1, which is equal to 2, plus sine x plus sine x, which is 2 sine x, all over our common denominator, cosine x times 1 plus sine x. Now notice we could factor out a 2 out of both of these groups here, and the way that would look is it would be 2 times 1 plus sine x all over our common denominator, cosine x, 1 plus sine x. And you can see that these are going to cancel numerator and denominator, the 1 plus sine x. We're left with 2 over cosine x, and remember, 1 over cosine is secant, so 2 over cosine is going to be equal to 2 secant x, which is what we were trying to prove that it's equal to. Okay, before we dive into problem number 4 here, we need to have a little bit of a heart-to-heart. Okay, so if you've stuck with me this far, I want to start sharing some little motivations and hopefully helpful hints here to help you to understand these identities. I know it can be frustrating for some students. It's like, what are you doing, Mario? What is all of this, right? Remember, an identity means that it's identical. Two things are identical. If they're identical, you can swap one for the other, okay? That's all that we're really doing. I'm going to show you where a lot of these trig identities come from at the end of this video if you want to stick around for that. But the key thing to remember is that what we're doing is like algebra, but with trig functions. Okay, so you've already seen me do getting common denominators. We did that in Algebra 1, right? You saw me do factoring. We did that in Algebra 1, right? So we're just doing basically algebra with trig functions. The other thing that you want to pay attention to is that you may not have seen a particular type of problem before. I may be showing you this similar type problem. When you see a problem that's like that again in the future, you're going to already have some familiarity. You're going to kind of know what to do. But I'm going to share with you what another teacher that I had before shared with me, and that's that if you don't know what to do, just make sure that you do something. You can't make a mistake. As long as the two quantities are identical, you can make a substitution, and you're eventually going to get to what it is that you're trying to prove. It might take you a few extra steps. Big deal, right? obviously want to get there faster if we can, but if it takes a few more steps, no problem. So let me show you another example. Hang with this here. You just have to keep practicing. It's going to get easier. So let's do number 4. Notice in this problem, we've got sine of negative x. This is what we call an even-odd identity. The sine of negative x is equal to negative sine of x. So let's make that substitution. This is equal to negative sine of x. So we're going to have cosine x in the numerator over 1 minus sine of x in the denominator. Now, we're trying to get it to look like this, right? What I'm going to do now is going to seem completely out of the blue, but you're going to understand in a minute. We've got this 1 minus sine of x. We're going to multiply by what we call the conjugate. Remember when you rationalized fractions that had radicals in them, like square roots, and you multiplied by the conjugate? So I'm changing this sign from minus to plus, but these two terms are the same. Whatever I do to the denominator, I have to do to the numerator, so I don't change the overall value of the fraction. So what happens here in the numerator, I'm just going to distribute. Okay, actually, let's see. Should I distribute? Yeah, let's distribute. So that's going to be cosine x plus cosine x sine x, right? In the denominator, we have a sum and difference pattern, which means that the inside, negative sine x, and the outside, positive sine x, those are going to cancel out. We've got 1 times 1, which is 1, and negative sine x times positive sine x is negative sine squared x. So you can FOIL that out or do the distributive property twice. And so now we've got 1 minus sine squared x. When I see the ones with the second degree, now it's not always this way, but a lot of times it's a Pythagorean trig identity. And you can see if I subtract sine squared x to the right side of this equation, 1 minus sine squared x is equal to cosine squared x. So let's go ahead and replace this with cosine squared x. So this is going to look like cosine x plus cosine x sine x, all divided by cosine squared x. Now, what I'm going to do is I'm going to split this up into two fractions. Cosine x divided by cosine squared x and cosine x sine x divided by cosine squared x. So if I do that, let me write it over here now, just we're running out of space. So with cosine over cosine squared, one of these cosines, actually let's do it in steps so we don't confuse anybody. So cosine x over cosine squared x. Okay, plus cosine x times sine x, all divided by cosine squared x. Okay, so that's all we did is we split it up into two fractions with the same denominator. One of these cosines cancels with one of these cosines, leaving us with 1 over cosine x. Over here, one of these cosines cancels with one of these cosines, leaving us with sine x over cosine x. Now we know the reciprocal of cosine, 1 over cosine, that's equal to secant x. Sine over cosine, this is our quotient identity, that's equal to tangent x. And you can see that's what we were trying to prove here, secant x plus tangent x, and you got it. Okay, see if you can pause the video and do number 5 on your own. Here we have sine of pi over 2 minus x plus 1 all over 1 plus cosine of the negative x, and we're trying to show that equals 1. So if I was going to do this problem, I would notice I've got this pi over 2 minus x. That's a cofunction. Sine of pi over 2 minus x is equal to the cosine of x. So we can replace this whole quantity here with cosine of x plus 1. And then over here we have 1 plus cosine of negative x. That's an even-odd identity. Cosine of negative x is just equal to the same as cosine of positive x. So this whole thing is going to be 1 plus cosine of positive x. Okay, now you can see that addition is commutative, right? So cosine x plus 1 is the same as 1 plus cosine x. Anything divided by itself is equal to 1. So you can see 1 is equal to 1, and we proved it. Okay, see if you can pause the video and do number 6. This one, let's see, we've got sine x times cosecant x over 1 plus cotangent squared x, and we're trying to show it equals sine squared of x. So I notice I've got this cotangent squared of x, and usually when I see the ones that are squared, I think of the Pythagorean trig identities. 1 plus cotangent squared is equal to the cosecant squared of x. So we can replace this with cosecant squared x. And then cosecant of x, we know that cosecant of x is equal to 1 over the sine of x. Okay. That's the reciprocal identity. So sine of x, this sine of x you can think of as like sine of x over 1. So numerator and denominator, that cancels. That's going to give us just 1 in the numerator over cosecant squared x in the denominator. And we know that sine and cosecant are reciprocals of each other. 1 over cosecant is sine. 1 over cosecant squared is equal to sine squared x. And we proved it. Okay, see if you can pause the video and do number 7. Cosecant x minus cotangent x times cosine x is equal to the sine of x. So how would you prove that one? Well, let's see. If I was going to do this one, I know that cosecant is the reciprocal of sine. So this is the same as 1 over sine x. I know that cotangent, using this quotient identity, is equal to cosine x over sine x times cosine x, which is kind of like cosine over 1, because anything divided by 1 is itself. So now let's see, we've got a common denominator. See, sine x, sine x. So I could really write this as one fraction with sine x as our denominator. And this is going to be 1 minus cosine squared x. Okay, now I see the one with the second degree, the squared. 1 minus cosine squared x. If I subtract the cosine squared x to the right side of the equation, that would be equal to sine squared x. So this numerator is sine squared x over sine x. One of these sine squareds in the numerator cancels with one of the sines in the denominator, leaving us with just sine x, which is what we were trying to prove, and you got it. Okay, see if you can do number 8. We've got cosecant x times cosine x over cotangent x plus tangent x, and we're trying to show it equals cosine squared x. Now, before you dive into that one, I just want to give you another hint. Sometimes students, they say, well, Mario, how did you know to use a particular identity, right? Well, if you ever get stuck, you can always convert things back into sines and cosines. Everything's built up of sines and cosines, okay? Those are the basic building blocks. So you could go back to sines and cosines, and if you're not sure what to do, and take it from that angle. And that's what I'm going to do in this problem. So I've got cosecant of x, which is really like 1 over sine of x, because sine and cosecant are reciprocals. Cosine x is just cosine over 1, because anything divided by 1 is itself. Cotangent x from our quotient identities is cosine x over sine x. And tangent x from our quotient identity is sine x over cosine x. Okay, so let's simplify down what we have here. We've got cosine over sine for our numerator, cosine x over sine x. And then in our denominator, we want to get a common denominator. So it looks like this one is missing a cosine. So let's multiply the numerator and denominator by cosine x. And over here, we're missing a sine. So let's multiply the numerator and denominator by sine x. So if we do that, we get cosine squared x plus sine squared x over our common denominator of cosine x sine x. Okay, now this is interesting. So when you have a fraction divided by another fraction, it's like multiplying by the reciprocal. So you keep the numerator. Let's just go up here for a little bit more room. So cosine x over sine x, that's our numerator. We're going to multiply by the reciprocal of the denominator, which is cosine x sine x. And then over cosine squared plus sine squared. But what's cosine squared plus sine squared equal to? 1. That's our Pythagorean trig identity. Okay, so now let's see what we have. Well, we have sine x in the denominator, cancels with sine x in the numerator. Cosine x times cosine x is cosine squared x. All over 1, anything divided by 1 is itself. And we proved that it's equal to cosine squared x. Okay, see if you can do number 9. We've got secant squared x minus tangent squared x plus cotangent squared x all over 1 minus cosine squared x. And we're trying to show that it equals cosecant to the 4th power of x. So how would you do that one? Well, I notice I have a lot of squares here. So when I think of the ones to the 2nd power, I think of the Pythagorean trig identities. And over here you can see secant squared minus tangent squared. If I subtract tangent squared to the right side of the equation, secant squared minus tangent squared is equal to 1. So I can replace this whole thing right here with 1. So that gives us 1 plus cotangent squared x over 1 minus cosine squared x. Now, if I subtract the cosine squared x, 1 minus cosine squared x is going to equal sine squared x. Okay, so it's a little bit more condensed. 1 plus cotangent squared x is equal to cosecant squared x. So another Pythagorean trig identity. And here's the other hint that I want to offer you, and that's that you want to keep one eye on the right side. You got to know kind of where you're headed, right? And the other eye on the side that you're working on. So as you're doing this, you're trying to think, well, I need to condense this somehow. Obviously, this is pretty condensed. But I also kind of use this as a guide. It's basically like they're giving us the answer. We know where we're headed, so we just have to keep our eye on where we're headed here. So now it looks like I'm trying to get to cosecant to the fourth. I've got cosecant squared, but I also have this sine squared. Now sine and cosecant are reciprocals of each other, right? You want to remember sine is equal to 1 over cosecant x. But if I have a sine squared, that's going to equal to 1 over cosecant squared. So that's what I'm going to do. I'm going to replace this sine squared with what it's equal to, which is 1 over cosecant squared x. Now, when you divide by a fraction, it's like multiplying by the reciprocal, right? So this is really going to be cosecant squared x, that's our numerator, over 1, times the reciprocal of the denominator, which is 1, that's actually cosecant squared over 1. So cosecant squared x over 1. And you can see cosecant squared times cosecant squared is going to give us cosecant to the fourth of x, all divided by 1. Anything divided by 1 is itself. And we proved it. Okay, we've made it to the last problem. So see if you can do number 10 on your own. We'll go through it together. Again, it takes a lot of practice. You want to do a lot of these problems to get good at them. So if you want more practice, I'm going to have another video at the end of this video that I'm going to reference talking about simplifying and verifying trig identities. I go through 14 examples in that video, so you want to check that out. And I'm also going to talk about how to understand some of these trig identities a little bit better, like I promised at the beginning. So we'll do that also after this problem. But let's dive into the last example. We're trying to show that this is equal to 4 tangent squared x plus 2. So what would you do in this problem? Well, to me, if I'm squaring something, that means that I'm multiplying it times itself. So this is really like tangent x minus secant x times itself. So another tangent x minus secant x. You might know the formula for squaring a binomial, but just some people, they kind of forgot. So you might want to just write that twice. So tangent x plus secant x times another tangent x plus secant x, right? So you can FOIL or you can distribute twice. So tangent times tangent gives us tangent squared. Tangent times negative secant x gives us negative secant x tangent x. Then negative secant x times tangent x is another negative secant x tangent x. So I'm going to write negative 2, okay? And then negative secant x times negative secant x is positive secant squared x. Okay, now over here, if we distribute tangent times tangent is tangent squared. Tangent times secant is secant tangent, and another secant tangent, which is 2 secant x tangent x, and secant times secant is secant squared x. Okay, so now let's see, we can combine a little bit. Tangent squared plus tangent squared is going to give us 2 tangent squared x, and negative 2 secant x tangent x and positive 2 secant x tangent x, those actually cancel because one's negative, one's positive. And then we have secant squared x plus another secant squared x, which is 2 secant squared x. Okay, now remember, we want to keep one eye on the right side. We want it to look like this, 4 tangent squared x plus 2. We've got 2 tangent squared x. How are we going to get rid of the secant squared x? Well, secant squared x is equal to 1 plus tangent squared x. So let's go ahead and replace this with 1 plus tangent squared x. And let's bring this down to tangent squared x. We'll distribute the 2. So that's 2 plus 2 tangent squared x. Bring this down to tangent squared x. So 2 tangent squared x plus 2 tangent squared x is 4 tangent squared x plus 2. And that's what we were trying to prove. And you got it. So Great job if you were able to get all those. Again, we're going to talk about how to do some of these identities or where they come from. And if you want more practice, go to the end of this video and check out that other trig identity video that I talk about where we go through 14 examples. So now on to the explanation of where some of these trig identities come from. You know, it's not absolutely necessary to know where they come from. I mean, they're identical. You can always interchange one quantity for another. And a lot of students are fine with just, you know, knowing that, right? But sometimes I find that if you understand where it comes from, you have all these formulas, but really when you understand it, you almost don't even have to memorize the formulas because it will make sense to you where all this comes from and why it is. And if you forget one of the formulas, you can quickly, remember what the formula is. So let's keep going if you're still here with me. So remember on the unit circle, it's a circle with radius of unit 1. And if you locate a point like right x, up y, that's the coordinates of the point. And say, for example, if you wanted to figure out like what's the sine of theta, sine of this angle. Well, you remember from trigonometry and even geometry, the sine is the ratio of the opposite side over the hypotenuse. So we say sine is y over 1, but anything divided by 1 is itself. So on the unit circle, we say the sine is equal to the y coordinate of the point, right? And the cosine of the angle is the adjacent side over the hypotenuse. That's x over 1, but anything divided by 1 is just itself, so that's x. And then the tangent, we know, is equal to the opposite over adjacent, so that's equal to y over x. Now, tangent being y over x, remember y is equal to the sine, and cosine is equal to the x, so tangent's really like the sine divided by the cosine, so that's where this is coming from, okay? And of course the cotangent, we know cotangent and tangent are reciprocals of one another, so that's how you're getting the cosine over the sine. Now for the Pythagorean trig identities, we know that a squared plus b squared equals c squared, right? So you have x squared plus y squared is equal to 1 squared, which is 1. But again, we've already established that the cosine is the x, so that's really cosine squared, and sine is the y, so that's really equal to sine squared is equal to 1. So that's our Pythagorean trig identity, this first one. But if we were to divide all of these by cosine squared, we're doing it to the left side and the right side to keep the equation balanced, right? What happens? We get cosine squared over cosine squared is equal to 1, plus sine squared over cosine squared is equal to tangent squared, and 1 over cosine squared is equal to secant squared. If you were to divide all of these by sine squared, you would get you would get 1 plus cotangent squared is equal to cosecant squared. So as long as you divide them all by sine squared or all by cosine squared, you get the other two Pythagorean trig identities. Okay, now for the cofunctions, let's look at this a little bit closer. So say if you have a right triangle like this. Say if this angle is theta, this angle has to be 90 minus theta, or in radians that's pi over 2 minus theta. Now just follow me for a moment here. So say if this is A, B, and C. So if I say what's the sine of theta, that would be opposite over hypotenuse, right? So sine of theta is A over C. What happens if I do the cosine of 90 minus theta? That's the adjacent over the hypotenuse. That's also A over C. So you can see that cosine of 90 minus theta is the same as sine of theta. And you'll see that's the true for all of these cofunctions. The sine and cosine go together. The tangent and cotangent go together, the secant and cosecant go together. And the reason is you're switching positions on this triangle. Like if you're over here and you're saying like, oh, what's the tangent? That's opposite over hypotenuse. But then if you switch to this, so that was A over B, right? So if you switch to this angle, you say, what's the cotangent of 90 minus theta? That's adjacent over opposite, that's A over B. And you can see they're equivalent, but you're changing the angle that you're working with to the other acute angle. So that's where the cofunction identities come from, and then, or a way to understand it at least. And then the even odd identities is like this. So when we go on our unit circle, we go this direction, it's a positive angle. When we go clockwise, it's a negative angle. So if I could draw the same triangle down here and say I make this a negative theta, this dimension here would still be x. This dimension on this triangle is going to be a negative y, and then the hypotenuse is 1. So say, for example, if I say, well, what's the sine of theta, this positive angle? That's opposite over hypotenuse. That's y over 1. That's y. But if I do the sine of the same angle but a negative angle, see sine of negative theta, that's opposite over hypotenuse. That's negative y over 1. Same y value, but it's the opposite sign. So we say sine of a negative angle is the same as the sine of the positive angle multiplied by -1. And you can see that's going to be true for the cosecant, the tangent, and the cotangent. But let's look at cosine for a moment. So cosine of theta is adjacent over hypotenuse. So cosine is x over 1. If you do this angle down here, the cosine of negative theta, it's adjacent over hypotenuse. It's still x over 1. So we say that cosine and secant are even, okay, functions, meaning that the cosine of negative x is the same as the cosine of positive x. The secant of negative x is the same as secant of x. Because remember, secant and cosine are reciprocals of each other. The odd ones are the sine, cosecant, tangent, and cotangent. And you're going to get the same trig function, but it's multiplied by -1. And you can understand it from drawing this triangle. So I hope that helps you to understand some of these identities a little bit better. Follow me over to that video right there where I dive into more examples of verifying trig identities, and we'll go through 14 examples. I'll see you over in that video. Great job.